All right, so we want to talk somewhat in depth now about electric flux and Gauss's law. All right. So the entire idea of flux is if I have, in this case, a field, okay, in this case specifically the electric field, piercing through some area. So if I have, you know, some pane, you can think of a window, you can think of light coming in a window, right? So all of the light that gets through the window contributes to the flux through that window, okay? And in this case, because we're thinking about electric fields, um, we're not talking about light, right? But you can visualize it with light if you would like. So the entire idea is that I have some source of field. I really don't care what that source is. Okay, it can be a charge or it can be a collection of charges. And in reality, in most situations, it'll be some sort of complicated collection of charges. I don't really care. Okay, all I care about is that there is some sort of collection of charge somewhere, and it's generating this field. All right, and I'm trying to evaluate something about this field by measuring how much field is captured by some area. Okay, that's the entire idea. Now, I'm going to draw this equation a little bit bigger over here. Okay, so the entire idea of flux, we give it the Greek symbol phi. Okay, the entire idea of flux is the product of the field times the area. Okay, and notice that I'm putting vector symbols here. Okay, now again, there are two ways to multiply vectors, and one way gives you a vector back, and the other way gives you a scalar back. And in fact, this is the scalar way. And so what this turns into is just the product of the magnitudes of the area times the value of the electric field penetrating through that area. Okay? And so the units are going to be the electric field in newtons per coulomb, and the area is going to be in meters squared. Okay, and so this turns into newtons times meters squared per coulomb. So this is the value of the electric flux. Okay, so don't get too wrapped up in the abstractness of this, okay? But this is abstract. You just have a generic area in space. It doesn't have to have a physical window. It doesn't have to be a physical pane. It is just some generic area in space in which you are evaluating how much electric field is penetrating through it. And that is the entire idea of flux. Okay. Oh, by the way, so remember that the direction that's associated with areas is perpendicular to the surface. So in this case, my area would have a direction parallel with the electric field. Okay. So when my pane is oriented such that the surface itself is perpendicular to the field, then we say that the pane itself is actually parallel with the field. The direction of the pane is parallel with the field. This is a little bit weird, but in formal mathematics, we define the direction of a surface to be normal to that surface. Okay? So don't get too wrapped up in that, but do realize that in this case, A and E are parallel. Okay, the direction of A is in the same direction as the field, and therefore the A and E vectors are parallel. Okay, So do be aware of that. And that will be important here in just a second, okay? So if we look at this next picture, we can see a flat plane back here, okay? And so this is very similar to the plane that we just saw, but it's also connected to another plane, and this plane is going to be at an angle, right? With respect to the first plane, and in fact, it is bent at an angle theta. Now notice, okay, both sheets, if I look at this from a side-on view, okay, I have something like this. So here's my first flat plane, and then it's connected to a slanted plane, and the electric field would be moving through it like this. Okay. And so you'll notice that here's my angle theta. Okay. And as we have in the diagram, the slanted surface is labeled as area A. And this surface is labeled as area A prime. And A prime, by geometry here, would be equal to A times cosine theta. Okay? And also notice that if my A prime and A planes are, pardon me, if they're at some angle theta with respect to each other, then that also means that if my plane A prime, okay, plane A prime has a vector direction this way, okay, then my vector A would have a vector direction this way. And the angle that this makes with respect to the electric field is also angle theta. All right? So what this means is that if the flux through these two surfaces is the same, the flux through A prime is equal to the flux through A, okay? Both areas are capturing the same number of field lines, in other words. Then what that means is that, remember from the previous slide, flux is given by the product of the electric field times the area. So this is going to be the value of the field times A prime, and that is going to be equal to the flux through this surface, which happens to be E times A times cosine of theta. Okay? So this is the formal definition of electric flux. This is the formal definition of electric flux. Okay? EA cosine theta. Now, for most of our purposes, we are going to be having our angles between the surfaces and the fields be 0, and therefore the cosine of 0 is 1. So in most cases, theta is going to equal 0, and therefore cos of 0 is going to be 1, and as a result, phi reduces down to E times A. Okay? But this is the general formula. Okay? This is the general formula. So do be aware of that. All right. So just a couple of quick kind of thought questions here. Calculate the magnitude of the flux of a constant electric field of 5 newtons per coulomb in the z direction through a rectangle with area 4 cubic meters, or square meters, in the xy plane. So if I think, let's see how well I can draw this. So here I would have my x-axis. I can have my y-axis here. And I will have my z-axis here. And I can think of a flat sheet in the xy plane sitting like this. If I can draw better. Let's actually do this in blue. So my sheet sitting in the xy plane is going to look like this, and it's going to be 2 meters on a side. Okay? And I'm going to have electric flux, or electric field, pointing in the z direction. So my electric field is going to be like this, moving through the surface. That's terrible. I am not the world's best perspective artist, as you're probably gathering. And the fact that I'm using a tablet does not make it any easier. But you get the idea, okay? So there is constant electric field penetrating through this area, and my field has the value of 5 newtons per coulomb, and the area is 4 square meters. Okay? And because, remember, the direction of my surface is perpendicular to the plane, so the direction of my area, is also going to be parallel, in this case, to the field. And when that happens, as we just saw, if the angle between the field and the area is 0, the cosine of 0 goes to 1, and my calculation just reduces to EA. Okay? So, what we can do now is we can say that the flux is equal to E times A, and that is equal to 5 newtons per coulomb times 4 square meters. And so this is going to be 20 newtons per coulomb times square meters, or newtons meters squared per coulomb. Okay? So 3 is the answer here. We will skip the next one, and this is one of the more important parts of Gauss's law. So remember that the electric field of a point charge is KEQ over R squared. So if this is a positive charge, let's draw these field lines, I will have electric field like this. Okay? And so what you can do is draw an imaginary surface. In this case, we call this a Gaussian surface. This is an imaginary surface. It is not a physically real thing. Okay? It is just an imaginary surface. But what you can do, and what Gauss's law allows you to do, is if you draw in this case, a spherical shell around a point charge. And the reason you want to draw a spherical shell is because the field is spherically symmetric. This is a spherically symmetric field. Okay? So my field is spherically symmetric. The entire point of Gauss's law, okay, is to try and evaluate what the field is at some point in space. Okay, so the claim is this, all right? We're going to do a little bit of mathemagic here. Well, not too much mathemagic, but just a little bit. So if we have the field of a point charge, okay, the entire reason I need to draw the surface is because to calculate flux, I need some sort of surface, okay? But the entire point of Gauss's law is that in this case, my surface is closed, okay? So your Gaussian surface is a closed surface. It's not an open surface like these panes are, okay? It is a closed surface. And you want to choose a surface that mirrors any symmetry of your charge distribution. So in the case of a point charge with spherical symmetry, you want to draw a spherical shell. Okay? And you want to center the charge at the middle of that sphere. Okay? So now the entire point is this. I want to calculate the flux through the Gaussian surface. Okay? This is the whole program. We want to calculate the flux through the Gaussian surface. And let's put a new slide in here. And let's get rid of all this nastiness. Because we're about to do a little bit of math. Okay. So I have my flux, or my field, is given by KEQ over R squared. And the flux is given by E times A. Now, you might be asking, if the entire point of Gauss's law is to find E, and I already know E, what am I doing? Right? So here's the point. What we're going to do is we're going to develop an equation that allows you to set EA equal to something, and then that equation, what we're about to develop, will be true for any situation, not just spherical point charges. Okay, and then we will actually apply it to a different situation. So the entire point is, even though I know E for this specific example, we can use that result to generate a machine or an equation that will allow us to then calculate the field in other situations. Okay, so that's the entire point. So the flux is given by the amount of field penetrating through the entire sphere. Okay, but the field is given by KEQ over R squared, and the surface area of a sphere is equal to 4 pi R squared. Okay, so what I'm going to have to calculate the flux is KE Q over R squared times 4 pi R squared. All right. And first things first, my R squareds are going to cancel, and this is going to give me 4 pi times KE times Q. Okay, now notice, this is a constant. What that means is, it doesn't matter how big your Gaussian surface is. If it encloses some charge, if some charge is inside your sphere, or inside your Gaussian surface, okay, if you have some sort of charge inside some sort of Gaussian surface, it doesn't matter how big or small you make that surface. As long as the charge is inside, then the flux will be the same. Why? So let's think about a point charge. Okay, so if I have a point charge, remember that the field will be strong near the point charge, and it'll be radially symmetric. And if I draw a Gaussian sphere around this thing, like say right here, imagine this is a sphere. Oof. Okay. Then my claim is this. If I draw more field lines, and remember that these are going to die off, they're going to get smaller as we move out, right? They're going to get smaller. So my claim is this. If I draw a second Gaussian surface, okay, if I draw a second Gaussian surface out here, these two fluxes are the same. Let's call the inner surface surface 1 and this surface surface 2. My claim is that the flux through surface 1 is equal to the flux through surface 2. And it's because this equation for the flux of a point charge is constant and it doesn't depend on position. Now in this case, okay, what's going on is S1 is smaller but the field that it's capturing is bigger. Whereas S2 is a bigger sphere. Let's use the phrasing larger radius. But the field at S1 or S2, gracious, I can't type today or write. So in one case, I have a larger field, but I have a smaller radius of my sphere. And at the second sphere, the field is smaller. It has a smaller magnitude since it's further from the charge. And so my field will be smaller, but my sphere will be larger. And so these two effects exactly cancel out to produce the same flux. Okay? So, what we can do now, all right, is say that phi is equal to 4 pi ke times q. Whoops, not g, but q. We're now going to define, okay, a new constant. All right? We're going to define a new constant. And what we're going to do is we're going to define this number, epsilon naught. It's called the permittivity of free space. Okay? The permittivity of free space. And I'm going to erase this over here since we already have it. And in fact, I'm going to erase the sphere as well since we already have it. If you need to recopy some things down, you can go back and back up the video. Okay. But what we do is we say that Coulomb's constant is equal to 1 over 4 pi times this permittivity constant. Okay? So in fact, the permittivity is more fundamental. Okay? The permittivity is more fundamental. And because it comes from this arrangement of Coulomb's constant, we can actually find its value by solving for it. And we get 1 over 4 pi times Coulomb's constant. So if I actually run the numbers here, what I find is that epsilon naught is equal to 8.85 times 10 to the negative 12th. And the units are exactly opposite of Coulomb's constant, so this is going to be Coulomb squared times newtons times meters squared. Okay? Now, why is this important? So remember that what we just showed was that EA is equal to 4 pi KE times Q. But now, if I insert this expression for KE in here, then I get, I'm also going to erase this. Okay. Once again, if you need that information, you can pause the video and back it up. But This is the entire point. Okay, this is it. This is the punchline. E times A is equal to 4 pi times Coulomb's constant, which is now written as 1 over 4 pi times epsilon naught times Q. But our 4 pi's cancel out, and EA, our flux, is equal to any charge inside our Gaussian surfaces divided by this new epsilon naught constant. Okay? So if you have flux and you have some sort of charge enclosed by a Gaussian surface, an imaginary surface, you can evaluate what that field is if you can measure the field and then add it up across the entire enclosed area. And if you have a flux, if you have a non-zero flux, your surface through which the flux is being measured has enclosed charge. Okay? So if you have non-zero flux, your surface has enclosed charge. So if I come back and look here at my Gaussian surface, right, we can definitely see that we have net flux outward because I don't have any field lines coming in. Whereas, in this case, they're all going out, and they're going to be spherically symmetrically distributed across that surface. So I could just add up all of the field lines, multiply that by the... Actually, I don't want to add up all the field lines. What I technically am doing, I would take a little slice or a little segment on the surface and evaluate the strength of the field lines coming out of that little segment, and then add up all of the segments across the surface, and that would give me the total flux. Okay, but Gauss's law is generalizable. Okay, so it doesn't matter what your charge distribution is, and it doesn't matter what the shape of your Gaussian surface is. You can have any shape you like. It just so happens it's easiest to do calculations with things like spheres and cylinders, right? But that being said, if I look at this kind of thing, where I have a charge and it's enclosed by an imaginary surface, the flux through that surface must be equal to 4 pi Ke times the charge, which we just showed reduces to the enclosed charge Q, divided by epsilon naught. So if I generalize this even further to have lots of positive charge, then my amount of charge would move from a lowercase small amount q to a large amount of capital Q, and my flux gets proportionally larger. Okay? My flux is just going to be proportional to the surface area. Or my flux is going to be proportional to the amount of charge. Sorry. Okay? So, that is the entire idea of Gauss's law. Okay? What Gauss's law in a deep sense is telling you is that because enclosed or inside charge causes an electric flux, The only way you have electric flux is if you have electric field. So what this is really telling you, Gauss's law in a deep sense is telling you that enclosed charge, or charge inside a Gaussian surface, is the thing that's responsible for any electric field in that, or in that area, in that region. Okay? Electric charge creates electric fields. This is what Gauss's law is telling you. And in fact, not just create it, but I can actually usually calculate this for certain cases. Okay? Now, in a really weirdly shaped Gaussian surface like this, I wouldn't want to do the calculation. It would be terrible. It would be horrible. But spherically symmetric and cylindrical is perfectly fine. And that is where we're about to go. Okay? So that is where we are going to head. So why am I worried about this whole enclosed or inside idea? Okay, let's pause for just a minute before we move on and talk about that. So imagine if I have a box, all right, and I set that box next to a positive charge. And I look at the field lines created by that positive charge, and my field lines are going to do something like this. Okay, and you'll notice some of the field lines are penetrating through the box, but for each field line that's penetrating, there's a field line that's leaving. So if Q is not inside, your net flux is 0. Okay? So only charges that are inside contribute to your net flux, right? But you can evaluate the field they are producing. That's the whole point. Charges inside some imaginary surface create a flux on that surface. If you can measure that flux, you can infer something about the electric field, or vice versa. If you can measure the flux and that tells you about the electric field, that actually tells you about the charge inside. Okay? So Gauss's law is reversible in that sense. So just as another really quick example, okay, find the electric flux through the surface of the figure below. The entire program that we just argued is that it's only Q inside that contributes to flux. So my Q inside is going to be equal to -5 plus -3 plus 2. And so this is going to give me -6. Okay? And these are in coulombs. And so the flux being equal to my Q inside divided by epsilon naught, this is going to be -6 coulombs divided by epsilon naught, or option 4. Okay? Now, couple of things, and we will get to the absolutely main punchline for the lecture. But that, to start, we made the claim in lecture that the electric field inside a conductor is 0, and we can actually now give a physical argument why. If I have a conducting shell with charge on the conductor, and we're going to let the total amount of charge on the conductor be capital Q, if I draw a Gaussian surface inside the shell, there is no charge enclosed or inside that Gaussian shell. if there's no Q in, there's no flux. No flux. Whoops. No flux means no E. Okay? So inside conductors, once the net charge has distributed itself across the surface, as we argued before, you can draw any Gaussian surface inside underneath the very top layer, and it will not enclose any charge. If it doesn't enclose any charge, you will not have any flux and you will not have any field inside. So this justifies the statement that no E inside a conductor. But if I draw a Gaussian surface outside at some radius r that's bigger than my outer radius of my shell, then I will certainly have electric flux through here, and I will measure EA equals Qn over epsilon naught. But again, if my shell is spherical, then my Gaussian surface, it would make sense to be spherical. And I can write down the surface area of a sphere once again, the surface area of my Gaussian surface. And E is equal to Qn divided by 4 pi times epsilon naught times r squared. This is the electric field of a point charge. Now, we've usually written it as E equals KE Q over r squared. But KE, remember, is 1 over 4 pi epsilon naught. So 1 over 4 pi epsilon naught is indeed KE. So these two formulas are telling you the same thing. Okay? These two formulas are telling you the same thing. Now, another type of surface for which Gauss's law is easily calculable is the sheet of charge. Okay? So think of like a long sheet of aluminum foil, for example. Now, if I have a sheet of charge, and let me look at this kind of edge on instead of more face on. Okay? If I have positive charges like this, okay, let's look at the field from this point charge. The field from this point charge is by itself would be like this, right? Actually, let me draw this in blue. It'll be easier to see what we're about to do. So if I have electric field from this point charge, and my electric field would naturally point like this. The point being this. Number one, these horizontal field lines really can't exist in this situation because, remember, the field lines from the other charges are going to be playing a role. And in fact, the field lines from my any given individual point charge are going to be scrunched up when they are close to other charges with like sign. But the point here being, if I have just an isolated point charge, you'll notice that if I look at these two field lines right here, and remember, these are spherically symmetric, okay? So I have field lines pointing in all directions with this magnitude at this distance r. Man, that's terrible. At the same distance r from my charge itself, right? At this distance r, the field is going to be identical in magnitude, but this field line has a horizontal component here, this field line has a horizontal component here, and these two horizontal components will cancel, and it will be left with the vertical components. And so I'm only going to get field in the vertical direction with a sheet of charge as a result. Each of these charges, and remember, the situation gets even worse with 2-point charges like this because the fields do this kind of thing. And when you do this kind of thing, it's even easier for your horizontal components to cancel and your vertical components to add. So the net, if I have field lines in my sheet doing this kind of thing, the net is only vertical. You cannot have a horizontal component to this field. All of your horizontal vectors are going to cancel out. Okay? Now, how can I apply Gauss's law here? What you do is you draw a Gaussian cylinder through the sheet. And that's what we have right here. Okay? So, this is a side view of this cylinder right here. And you'll notice it's kind of hard to see, but it does go through the surface onto the other side. Okay, so I have part of my cylinder poking up through the top of the sheet and part of the cylinder poking down through the bottom of the sheet. But remember, the argument is that only my vertical components have a net value. All of the horizontal components cancel. So my electric field coming off of my sheet is only going to be vertical. As a result, okay, I will not have any flux through the sides, only the two circular faces. Only through the two surfaces that are labeled area A. Well, this one's already labeled, right? So we've already labeled our area here as A, right? So this would be A right here, and this would be A right here. Okay, so I have two surfaces that are capturing the flux, and so the total flux is equal to the amount of field being captured at the distance away from the sheet by either area, and I have two total areas, or two of my circular faces contributing to my total area. So this is the area of each circular face, and 2A would be the total area that's capturing flux, and this must be equal to the charge inside, any charge enclosed within the Gaussian surface, this is my Q right here, divided by epsilon naught. Okay? And so, as a result, what I can say is that my field, let me erase our dipole field picture. What I can say is that my field is then equal to my enclosed charge divided by 2 times epsilon naught times A. All right? But what I can do at this point is I can define a new quantity called charge density. And I have, in general, 3 different types of charge density. I can string charge along a wire, and this would be called charge per unit length. If I distribute charge along a wire, if it is charge along a sheet, this is charge per unit area. And if I were to have some volume of charge, like a sphere, it would have to be an insulating sphere because, of course, the conducting sphere, the charges are going to gather across the surface. But in an insulating sphere, you can have charge inside or throughout the interior. And if I have that, then this would be charge per unit volume. We give the charge per unit length the Greek letter lambda. This is not important for us. I don't think we're ever going to see charge per unit length. But charge per unit area is given as sigma. All right, and this is what we're going to use, and we're actually going to see this several times throughout the semester. So it's worth understanding at this point. Charge per unit volume is usually also given by the Greek letter rho. So you'll notice all of these are Greek letters, right? Lambda, sigma, and rho. For our purposes, sigma is the most important. So why is this important? Well, so you'll notice that I can rewrite now my formula for the electric field as my charge over my area, but that is my charge density. Okay? There are no spatially dependent variables in this equation, so this means that this result is constant. There is a constant electric field when working with sheets. Now, technically, this result of a constant field is applicable for a truly infinite sheet of charge. Okay? A truly infinite sheet of charge. However, if you're near a large sheet of charge, if you're near the center, then any effects that you would see, any fringe effects toward the edge, you don't really experience. And so effectively, if you're at the center of a large plate of charge or a large sheet of charge, you're still going to experience this more or less constant field. Okay, so this is a really good approximation for certain circumstances. Not the least of which is one of the most important things we're going to study this semester, which is the capacitor. Okay, so what we have here, if you have 2 plates of equal and opposite charge. This is the basic idea behind the capacitor. Just a device that stores charge. Okay? But the entire idea is this. If the field coming from this plate is like this, and this plate would have strength E equals sigma over 2 epsilon naught, but the negative plate would have similar arrows pointing directly toward it. And so remember, electric field lines can't cross, they can't crisscross applesauce, but they can merge. Okay? So basically, these field lines are now going to merge into one field. And if both plates are contributing sigma over 2 epsilon naught, then when they add together, right, the negative plate is contributing the same amount if we assume that it has the same amount of charge and their areas are the same. So these are identical plates just with equal and opposite amounts of charge. Then each field individually is contributing sigma over 2 epsilon naught. And so the total field, because these fields merge, the total field is given by E equals sigma over epsilon naught. So in between two charged plates, the field is equal to E equals sigma over epsilon naught. Now, the claim here is that the electric field is zero on the outsides of the plates. Why is that? Because if we consider these infinite sheets, then because this field is constant, it will also have constant value everywhere. Right? It'll be like this. But the negative sheet has constant, not downward there. It will have constant electric field pointing toward the plate on the outside. And each of these vector pairs will cancel out. And that leaves your field at zero. The same argument holds for the plates on the other side. Now, this is not strictly true when your plates are finite. And as far as we're concerned, our plates that we're going to be thinking about inside our capacitors are going to be rather small. Okay? But compared to an electron, it is super huge, and very near the surfaces, these approximations are true. The electric field is constant between them, with value sigma over epsilon naught, and outside the plates, if you're very close to the plates, outside the plates, the field is effectively zero. When you get to the edges, okay, you get some kind of weird fringing effects. The fields kind of go like this, and then they start to do those butterfly things that we've seen. And so these are not constant field lines in the same way that the field lines in the center are. But if you're near the center, then this is effectively approximated by a infinite sheet, and your individual sheets will have their formulas like this, but their sum will be given by that. Okay? So, keep this in your back pocket. The electric field of a sheet of charge is constant everywhere, and if it's infinite, and the value is given by the charge density. The more charge I have in some area, the stronger my field. That makes sense. Divided by 2 times epsilon naught. This is for a single sheet. When I have both plates together, or both sheets together, then both halves make a whole, and I get sigma over epsilon naught. Okay? So this is for your single sheet. This is for your equal and opposite charged sheets. Okay? All right. That is Gauss's law, and that is the major result that we need. So, I hope you found this useful, and we will see you later.